Right, any questions from what we have discussed up to now?
Excuse me, sir.
Yes.
When the whole building subjected to a twisting moment, there's a chance for the column to get that twisting. No?
No, actually, that's not what happened. I'll explain it.
Okay.
So basically, what happens is you take a building. Let's take that we are having some shear walls like this, and we are also having some other shear walls like this. So let's say the building, then there are columns. So if you look at, so there are columns and shear walls. So when these subjected to twisting moment T, so there are columns and also you can see there are shear walls. So if it is subjected to a torsional moment T, then what happens is these columns will not be subjected to a torsional moment because the twisting is controlled by these elements. The shear walls are controlling the twisting. So due to twisting moment, this shear wall, so twisting this way occurs due to wind load this way. So due to this wind load, this particular shear wall will be subjected to a load this way. And in addition to this, we have a twisting moment. Due to twisting moment also, there will be another load this way. So what actually happens is this twisting moment is now resisted by a couple of forces. A couple of forces. There is a twisting moment. So this acts this way. So it will be resisted by two loads like this acting at an eccentricity x. We are acting with with a lever arm x. So that's what happened. So basically what you see is, although the full building is subjected to torsion, it is resisted as lateral loads acting on two or more shear walls. So because it's resisted by the shear walls with a lateral load acting, you can see individual elements cannot go into torsion because they are not going to resist this torsion. So that's why we say, although the building is subject to twisting, individual columns will not be subject to twisting because this torsional moment is not resisted by the individual elements. It is resisted by the shear wall. Again, the shear wall will also not be subject to torsion because shear wall resists the torsional effect in the form of in-plane loads. So the shear wall will be subjected to, one shear wall will be subjected to a load like this. The other shear wall will be subjected to loads like this. So the net effect is, we have the shear wall subjected to lateral load and the same shear wall subjected to lateral load due to torsional effect, and the shear wall on the other side same, but that shear wall will be subjected to load in the other direction. So you will find this shear wall carry F1 plus F2. This shear wall will carry F1 minus F2. So that's what happened. So here this F1, F1, F2. This is a simplified view, not the exact view, but this is how it happens. So here you get F1 is due to the lateral load, F2 is due to torsion effect. F2 is due to torsion effect. So even the torsion effect is a lateral load, lateral in-plane load on the shear wall. So because of that reason, the individual elements are not going to resist any torsion, and not even the shear wall is going to resist torsion. And only shear walls that will resist torsion will be the shear wall assemblies. So if you have a shear wall arranged this way, then this kind of assembly which is closed with a beam can resist torsion. So this can resist torsion with the assembly. Otherwise, all the torsion will be resisted by individual elements. Is that clear?
Yes, sir. Clear. Thank you.
Is that clear? So the torsion is not resisted by columns. Torsion is not resisted by shear walls unless it's an assembly. So all these are resisted as in-plane loads acting in the lateral direction. In-plane loads acting in the lateral direction. I think that's clear. Is that right? So in addition to that, again, slabs acting as rigid diaphragm also helps in this particular action, because all the elements will now behave in a particular way because of the slab which acts as a rigid diaphragm in that particular level. Now let's look at, when we make a three-dimensional model of a building, what's the type of information we can gather from a 3D model? So when you make a 3D model, you will have columns, beams, slabs. You can even have transfer floors, and if you want, you can even model the foundation. So when you do all this, you can get some useful information once you do the analysis. And the first thing that you can get is natural period for any number of mode shapes. So natural period of vibration for first mode, second mode, third mode, all can be obtained. But when you are calculating the natural period of acceleration, you have to be careful, because you are now following dynamics. You have already followed dynamics. You know the natural period of vibration depends on the mass of the structure. Mass of the structure. And mass depends on, what the mass you have asked the program to take care of. So if you look at the structure, then first thing you see is, the structure consists of the elements where because you have modeled the actual size of the element, the program automatically takes care of it by calculating the weight of the structure for the vertical load calculations, and calculating the mass of the structure for the calculation of dynamic properties. But in addition to this permanent load, which is the self weight, you get other loads, permanent loads. You get other permanent loads. They are due to the services, finishers, and then partitions. All those things are permanent loads. But unless you specifically allocate these to the mass, then the program might not consider that this mass exists. So when you are doing a 3D model, it's very important that we allocate the mass source properly, so that the natural period of vibration that the program calculates will be reasonably accurate. So when we do modeling, I'll show you how to do that, and I'll show you how to do that on SAP 2000. But you can try that on any other program that you are doing, but using. But if you know how to do, why we are doing that using one particular program, you can always do the same thing in any other program as well. So basically, when you are calculating the dynamic properties, it is very important to consider the actual mass available at each floor level. And the actual mass available at each floor level will not be only due to the dead weight of the structure. It will be due to superimposed dead loads as well. And if you want, you can even consider portion of the live load as well when you are calculating the natural period of vibration of the structure. And when you have a 3D model, you can perform the structural analysis for lateral loads, that is earthquake analysis and wind analysis. So once you perform the earthquake analysis and wind analysis, and all the vertical loads are also applied, then you can find the load on the columns, loads on the walls, loads on diagrids, transfer plates, pile caps, piles, all can be found by using the 3D model. The reason is any vertical load due to the permanent loads and also the vertical loads due to lateral loads, all will be represented properly by in the 3D model. But what you can't find from a 3D model is what is the bending moment in slab. Generally, you can't find it on a 3D model unless you have specifically done something special to find it. And you cannot, generally we don't use the 3D model to find the bending moment on beams. The reason is in the 3D model, we don't represent the pattern loading. So without the pattern loading, it's difficult to find the exact bending moments for the beams. So because of that reason, we generally don't use a 3D model to find to design the slabs and beams. But you can design almost every other element by using a 3D model. You can design almost every other element by using a 3D model. And how do you design the slabs? Generally, you know, one-way or two-way slabs we can easily design by using yield-line normal theories or yield-line method. One-way and two-way slabs. One-way slabs can be considered as a one-way spanning beam, and then by considering 1 meter width, you can design it. In the case of flat slabs, you can design the flat slab separately without worrying too much about the columns and all that. So you can do a flat slab. If it is solid slab, two-way spanning, you can use yield-line theory and design the slab. At the same time, if you want, you know, you can model the slab using shell elements and get reasonable answers. But you have to ensure that, you know, you have allowed for cracked sections. So the cracking of the section has been allowed. So when it comes to beams must be designed to resist the pattern loading. So you will go for a subframe analysis as I have shown today. And when it comes to columns, and you know that, you know, when you are doing analysis, we allocate a reasonable live load, and that live load has a factor about 50% allowance for the dynamic nature of the live loads. So basically, when you are designing an auditorium with fixed seating, or if you are considering an assembly hall or a lecture hall without fixed seating, in the second case, we'll use a live load of 5 kilonewtons per meter square. In the earlier case, we'll use a live load of 4 kilonewtons per meter square. For fixed seating, we use a live load of about 4 kilonewtons per meter square. For without seating, fixed seating, a hall, we'll use 5 kilonewtons per meter square, considering the fact that it can be used for activities like dancing and so on. Then the maximum load that you can get on the slab is about 2.5 kilonewtons per meter square. But when you are designing, we design it for a load of 5 kilonewtons per meter square. So you can see the live loads that are allocated has an allowance of about 50% for dynamic effects. So when you are considering the full building, you can you don't have to consider this dynamic effect, because there's no chance that all the structures will have dynamic loads at the same time. So what we do is, we know if we want, we can actually reduce the vertical load that we allocate by actually reducing the adjusting the factor of safety that we use for live loads. For example, if you can make 40% reduction in the live load, then instead of allocating 1.5 for the live load factor, what we allocate is 1.5 into 0.6. 1.5 into 0.6. Because if you allocate a 1.5 factor, then you are considering the full load. But what you want is 40% reduction, which means you have to multiply 1.5 by 0.6. So for the live loads, you lose a factor of 0.9 instead of 1.5. So basically, we have to consider the possibility that all the floors will not be loaded simultaneously. And because of that reason, we can have some reduction for the live loads when you consider the full building and doing a 3D model. And the kind of live load reduction that we do for all the columns will be applicable for piles as well. So even the foundation, we know that the full building cannot be loaded fully to the capacity of the live loads that we have considered, because all these live loads contain an allowance of about 50% to allow for dynamic effects. So the actual live load that comes on the structure may be only about 40 to 50% of the live load that you consider based on various guidelines. So when you make a three-dimensional model of a building, you have to be a little careful. It doesn't tell you everything. It tells you the loads on the columns, it tells you the loads on the pile caps, piles, and it can also tell you the loads on the transfer plates, and what else? Yeah, if you have concrete walls, certainly the loads on the concrete walls also can be found from 3D model. But generally, we don't worry about the 3D model to design the slabs and the beams, and those can be designed independent, but you can use some of the results from 3D model when you are designing the columns, because columns will be subjected to axial load plus bending moment. So these bending moments can be obtained from the 3D model. So beams and slabs we design separately, but almost all the other elements can be designed by using the 3D model. Any questions on that? Anybody having questions? So the important points to be highlighted are that natural period of vibration will be accurate only if you have allocated the correct mass. Then 3D model cannot help you to design the individual slabs and beams, and those have to be designed separately. So this is one example of a 3D model of a building done using SAP 2000, and this is the normal line model, and this is the extruded model. And here you can see at this particular level, we are having fairly large transfer beams. Fairly large transfer beams are there, and the foundation has not been modeled. Only the structure, superstructure has been modeled. And you can also see above the transfer beam level, the columns have been discontinued. So these are the large columns, and those large columns have been discontinued. And then the structure contains shear walls, the short walls arranged in the upper level of the structure, so that the whole structure can be constructed with car parking in the lower levels and the apartments in the upper levels. But if you look at the shear core, you can see the core is continuous, because the core which is used in the car park levels are used at the upper levels as well. So how do you analyze the subframes? The subframes can be analyzed using pattern loading. Here you can see the same subframe, but different load patterns, And here you can see almost all are loaded fully. Here this span is loaded fully, but here this span is loaded minimum. And here you can see these two spans are loaded less, this span is loaded more. So this way you can create different pattern loadings and then end up with a bending moment in load. So to create a 3D model, as we discussed earlier, first you have to start with some member sizes. You have to start with member sizes. So how do you calculate the member sizes approximately? So that is the first question you have to ask. Because to create a mathematical model, first you need to have the architectural drawings for the building. Then you have to create a set of general arrangement drawings highlighting where you are going to get the beams, columns, walls, the foundation arrangement with pile caps and piles. So all those will be needed to create a model. So the first step in creating a model is doing the preliminary calculations. So how do you find the size of a column? How do you find the size of a column? To find the size of a column, as we had discussed earlier, we can go for this tributary area. As we have discussed earlier, you can go into this kind of tributary area. And once you use the load on the tributary area and multiply it by the number of flows, then you can make use of an equation like 0.4 FCU AC plus 0.75 FY AC. So what this means is these are the force in concrete, these are the force in steel. So the axial load carrying capacity is equal to force in concrete plus force in steel. Then you will ask, how do you get this equation? And actually this is the equation when you are dealing with cube strength. When you are dealing with cube strength, the equation is N is equal to 0.45 FCU, this is the concrete strength, multiplied by concrete area plus 0.87 Fy area of steel. So this is a normal equation. So, for steel, we use a factor of safety of 0.87. When you have a cube strength with all the factors of safety can be related to the cube strength. FCU can be related to the compression load carrying capacity as 0.45 times FCU. So this is the maximum capacity. So what we do is we reduce this capacity by 10%. Then you will end up with 0.4 FCU AC plus 0.875 FY AC. AC. So when you are using Eurocode, the axial strength is given by 0.567 FCK of FCK is the cube cylinder strength. Cylinder strength. So you can say when you are using Eurocode with the cylinder strength, you can say same equation 0.567 FCK AC plus 0.87 Fy AC. And if you reduce the kiss capacity by 10%, then 0.567 into 0.9. So you can use an approximate formula like N is equal to 0.51 FCK AC plus 0.875 Fy AC. So what we do is, for this area of steel, we say the area of steel is about 2% of concrete area or 1.5% of concrete area. So concrete area is AC. We say the steel area is about 1.5 or 2% of concrete area. So with this approximate calculation, we can find N value. We know the strength of concrete, we know the strength of steel, and only unknown is area of concrete. So we can straight away find the area of concrete. So this is the type of approximate calculation you will do to find the area of concrete when you are doing the approximate calculations to create the mathematical model that you like to use to represent the actual structure. So this is the type of simple calculation you can do. And if you are using cube strength, you will use this equation. If you are using cylinder strength, you will use this equation. So using one of those equations, you can always find the area of concrete needed. So that area of concrete can be arranged as a square column or a rectangular column. As a square column or a rectangular column. Is that calculation clear? How to find the size of the column at the initial stages where you don't have that information? So how do you find the thickness or the size of the slab or the thickness of the slab? Thickness of the slab is generally found by considering the deflection criterion. So something like the effective depth of the slab is equal to span divided by 35. Span divided by 35 will give you a reasonable value for the thickness of the slab needed. Something like 32 to 35 for reinforced concrete. For pre-stressed concrete, you can go for something value like span over 40, span over 40 or 45 for pre-stressed concrete. For reinforced concrete, you will go for a value like span over 32 to 35 to find the thickness needed for the slab. So how do you find the size of the beam in the initial stages? With these efficient lateral load resisting systems that we use, you will find that the size of the beam is about 600 millimeters depth, even for a fairly tall building. The reason is, if you try to use a beam of a depth more than 600 millimeters, then you will find that the flow-to-flow height has to be increased. Because when you consider the flow-to-flow height, the flow-to-flow height depends on the clear height that we generally like to be about 2.7 meters, then about 300 millimeters for the AC duct, and then the beam depth. So if you are going to have 0.8 meters, this will give 3.6 meters. If you are going to have 0.8 meters, you will end up with 3.8 meters. So what we generally do is, if the span is large, rather than, so generally we use a beam of 600 by 400. You will consider using the beam of 600 by 500. Something like that. You'll increase the width of the beam rather than increasing the depth of the beam. So that's one strategy that we use. And in the case of apartment buildings, you'll find that the depth of the beam can be about 500 millimeters. But in commercial buildings, the maximum depth is about 600 millimeters. You'll try to do everything possible to make sure the slabs can be supported within 600 millimeters. Otherwise, the flow-to-flow height will increase. So the width of this particular beam can be about 350 to 400, and that will allow you to do concreting properly. Otherwise, if the beams are thinner, then concreting will become difficult. And in the case of apartment buildings, we try to keep the beam depth around 500 millimeters. Not that you cannot go for 600, but generally we try to maintain it around 500 millimeters. So how about the wall thickness? Wall thickness minimum is 200, but preferred thickness can be about 250 or 300, because those can be cast easily. And also we need to provide some additional reinforcement in the form of links at the top of the walls, top of the columns, and bottom of the walls and bottom of the columns to provide additional ductility. And in addition to that, in columns and walls, it is possible to, it's better to use high yield bars as the links than mild steel. The reason is, in case of earthquake situations, mild steel tend to yield easily, and the moment the steel used for link yields, you will find that the confinement offered to concrete reduces, so concrete can crack and crush. So to prevent that happening, better to use high yield bars. And if you want to save steel, then you can use 8 millimeter links than 10 millimeter links with high yield bars, than using my steel for steel reinforcement, the links. And if you look at Euro code, my steel is not allowed, and what is allowed is only the high yield bars. But in Sri Lankan context, you might still find my steel has been used, but generally the 8 millimeter high yield bars would be better in columns and columns, beams, walls subjected to earthquake loading. So any question on this particular slide? So I have explained how to calculate the column size, the reasonable rule for slabs, and then the beams size. How do you select the beam size? And again, you know, if the spans are large, you have to carefully check the beams for deflection as well. But generally, deflection is not a major problem in beams, because if the spans are small, then beams will be fairly safe. But if the spans are large, you have to be extra careful with the deflection of the beams.